In this video, we're going to talk about harmonic functions. Now, this is part of a complex analysis playlist. I'm not going to mention anything about complex analysis in this video, though. So here's our setting that we're going to start with. We're going to start with differential equations. So to remind you what those are, what we do in differential equations is we study the relationship between functions and, one, their derivatives of any order, like first derivative, second derivative, whatever. So for some, and these are called ordinary differential equations, or ODEs for short. For some examples of these, maybe something like, what functions y satisfy the equation y prime equals y? What function is equal to its own derivative? Or what family of functions equals their own derivative? And I know that that is a model for like simple population growth. Another example is, what functions y satisfy y double prime plus 4y equals sine of x? And you might recognize that if you've had diffie-q before, as this is modeling a mass spring system with some kind of external forcing. And so, again, all I'm trying to do is illustrate some kind of relationship between a function y and any of its derivatives, or any of its derivatives and some other functions we've got. So that's one thing you study in differential equations. Another thing that you might study is a relationship between your function and maybe its partial derivatives, if you've got a function of multiple variables. And so these are called partial differential equations, or PDEs for short. So to give you an example, what functions u satisfy, well, the partial of u with respect to t plus u times the partial of u with respect to x equals some constant nu times the second partial of u with respect to x. And this is a famous one that's called the viscous-Burgers equation. It's important in like fluid mechanics. So a famous PDE, another famous PDE, I'm just name dropping diffie-q's on you. So another famous PDE is Laplace's equation. And I'm going to write down the two-variable version here. So it looks like the second partial of f with respect to x plus the second partial of f with respect to y equals 0. Now functions of two variables, that's our solutions to Laplace's equation here, that also have continuous second partial derivatives. So these two things, a solution to Laplace's equation and a function f that has continuous second partials, those are going to be what are called harmonic functions. And again, that's what we're going to look at in more detail in this video. So let me give you an example of a harmonic function. Something innocent from like Calc 3, somebody like f of xy is x squared minus y squared. This thing's harmonic. And so let's just check. When I take the second partials and add them together, do I get 0? Well, when I take the second partial of f, I get 2, and the second partial with respect to y, I get negative 2. When I add those together, yep, I get 0. So that function's harmonic. Now let's look at some vector calculus to help us understand why are harmonic functions, why are they cool? Why are they worth studying? And so one concept from vector calculus that we need is the gradient. And so the gradient of a function is a vector field. So if I take the gradient of this guy, x squared minus y squared, it should be the vector field whose components are the first partial with respect to x, and its second component is the first partial with respect to y. Here, this upside down triangle, or if you're a LaTeX user, /nabla, that is the symbol for the gradient here. So I just make a vector out of its first partial derivatives. And in this case, when I do that, the first partial is 2x, and the partial with respect to y is negative 2y. So that there is a vector that's called the gradient. I'm using this angled bracket notation also for vectors. If you come from using i's and j's or like hats, like that's the same thing. So I'm just using these angled brackets to denote a vector. Another thing, these angled brackets denote column vectors, and that's going to be important because we're going to talk about some matrix multiplication in a few seconds or minutes. Now, what does this vector, the gradient, tell us about? Like, why do you study it in a Calc 3 class? Well, the one thing it tells us is it tells us the direction in which the values of your function f change the most. So like, which way do you point to get the most change out of your function? So to give you an example with the function x squared minus y squared, when you graph that, you get this 3D saddle looking thing. And at the point 1, 2, and so really, when I plug those in, I get negative 3 as the z-coordinate. What the gradient tells me is which way should you face so that you have kind of the steepest climb up the saddle or the steepest run down the saddle, depending on which way you're going. And in this case here, I should point in the direction of the vector 2, negative 4, and that's that black vector there that I've labeled for you in orange. So if you start there where that black vector is and you point along that black vector, that'll give you the steepest climb up the saddle. The other thing that the gradient tells me is what is the maximum rate of change? So like, what is kind of the slope there if you point in that direction? And how you calculate that is it's just going to be the length of the gradient, the magnitude of the gradient. So like for this little running example that we have, at that point 1, 2, when x is 1 and y is 2, the maximum rate of change if I go along that black vector is going to be just the magnitude of the gradient, 2, -4. And remember, that's just the distance of that point from the origin, if you like to think of it that way. And I think if I reduce that and did that algebra right, should get 2 times the square root of 5. All right, so another concept from vector calculus that we need to be familiar with is the divergence of a vector field. So if you're given a vector field f, where the components of this vector field are, two functions g and h that depend on where you are in the plane, say, so depend on x and y, the divergence of this vector field, I'm going to denote it by div for div f. And what you do is you still take the first partials of your functions, g and h, but just the partial of g with x and just the partial of h with y, and you add it together. And notice here that like both of those things, when you plug a point x, y in, these things are going to be numbers. So like the div, the divergence, it's kind of a measurement of something. So what is the divergence of a vector field actually measuring? It measures something called the flux of the vector field away from that point x, y. So kind of like, how is the vector field f kind of moving points toward xy or away from xy? We're going to use the word sources and sinks in a moment. So it kind of measures that change around that point. Is it pulling points towards it? Is it moving points away from it? So that's the divergence. Now, what if it's doing neither one? So like, what if it pulls as many points towards it as it does push away from it? Think of it that way. Then when the divergence of f is 0, we're going to say f is, one way to say it is divergence free, transverse, incompressible, or solenoidal. And all of these things are synonyms to each other, just depending on what book you use, they might just pick one of these words. So like incompressible, I think is popular in, again, like a fluid mechanics background. All right, so then what does that mean? When the divergence is 0, that means that this vector field has no sources and no sinks. So there are no spots where it pulls more points toward it than it does push points away from it, and vice versa. And so just to give you some pictures again, what do I mean by pulling towards or pushing away? Here, I have this vector field and the arrows are plotted, and the origin is a source, right? It's always pushing points away from it. That's what the arrows indicate. And a source has positive divergence. A sink is here the origin. It's not labeled in red, sorry about that, but the origin is a sink here because you can kind of see it's kind of swirling around the origin. So the origin is pulling, this force is kind of moving points towards the origin. And the last thing, if it's solenoidal, is this one, so 0 divergence. So here, there are no sources and no sinks. So there's still kind of like a spiraling around, but it's not kind of going toward the origin. It's not falling in, right? It's always consistently just going around, neither getting bigger or getting smaller as you traverse one of these little circles. Okie dokie. So what we're going to do is we're going to put these concepts of gradient and divergence together. So what do I mean? So if I had a scalar function f of two variables x and y, I can take the gradient, and now I've got a vector field, and I can take the divergence of that. So we're going to take the divergence of the gradient. So I'm going to take div of the gradient of f, and I know that that's div of this vector here. And remember, what does div do? Div is going to take the first partial with respect to x of the first slot plus the first partial with respect to y of the second slot. Well, like if I differentiate the first slot again, I get the second partial of f with respect to x. And if I differentiate the second slot of the orange vector with respect to y, I just get the second partial of f with respect to y. And that should look pretty familiar to you. And I'm going to make it more apparent in just a moment. Now, what does this measure? Well, the divergence measures the flux of your vector field. So this measures the flux of the gradient of f away from the point x, y. But it's not super clear like what that means. If you can make sense of that, fantastic, good for you. But if you feel like, oh, I'm not sure what you're saying to me, what should I take away from f there? We're going to get to that. So we're going to give this a name. We're going to call the divergence of the gradient, we're going to call that the Laplacian of the function f. And so what we've got then is we can say that a function f is harmonic whenever its Laplacian is 0, right? Whenever the divergence of its gradient equals 0, and also whenever its second partials are continuous. Now, notice here, to bring in another class, it's always nice to see how a lot of these math classes are related to each other. Like you've seen from like Calc 3 or multivariable calculus, something called the Hessian. And the Hessian was the matrix of the second partial derivatives. And you might notice that the Laplacian of your function is just the trace of the Hessian. And remember what the trace is just when you add together the diagonal values. We could tie that back into some more linear algebra, right? Where like the sum of the diagonal values are exactly what the eigenvalues add up to. Another thing too, if I know that the second partials are continuous, then I know that the mixed partials like fxy and fyx, those are the same. And so I've actually written that when I've written down the Hessian there. I just went ahead and put fxy in both. And remember, a matrix where the kind of off-diagonal entries, when you just switch the indices, whenever those match, that's called a symmetric matrix. So in this case, the Hessian should be a symmetric matrix whenever you're dealing with, again, a function whose second compartials are continuous. Okay, so we've kind of gotten a little bit off task. Why are harmonic functions cool? So let's fix a point in the plane x0, y0, or x0, y0, and let's fix some positive number epsilon. And let's let xy be any point that's inside the circle centered at x0, y0 of radius epsilon. So I've got a little picture over here. So x0, y0 is the center, and xy is just some other point inside this little circle. And what I'm going to do is I'm going to call kind of the circle and its inside, that's a region, we're going to name it R. So you might call that a disk. So I've got this disk R. Now, what we want to do is we want to talk about like how is a function, a nice enough function say, how is the value of that function at the center related to the values near it, say other values in this disk? And Taylor's theorem gives me a way to answer that question. Taylor's theorem tells me that the value of my function at xy, it's related to the value of my function at the center of this little disk. And I'm using this approximation symbol here. I know that the value at xy is approximately equal to the value at x0, y0 plus the kind of, first order differential term. So in my case for this multivariable stuff, that will be the gradient of f evaluated at the center, dotted with this vector x minus x0, y minus y0. And then I'm going to do like a second order approximation. So like in Calc 1, you have like a second derivative term. Well, in multivariable calculus, like your second order differential thing is going to be the Hessian. And the way that it's written is going to be 1/2 times, I'm going to take x minus x0, y minus y0, the transpose of that vector, that's what the t means, times the Hessian, times my vector x minus x0, y minus y0. So again, this is just sort of like the second order Taylor polynomial in the multivariable case when you've got two variables. By the way, those last three terms there, that's a 1/2 vector times a 2/2 matrix times a 2/1 vector. And so that makes sense to multiply. You can check when does it make sense to multiply matrices. And when you do that, you should get a number out of this. So that's good. That means it's a function. Now what we're going to do is, so I've got this expression for approximately what f of xy is. We're going to just go ahead and integrate both sides of this over the disk, over R. And so all I'm going to do is I'm going to take the double integral over R. Remember, dA is just either dx dy or dy dx. And, you have to make a choice which one it is when you go to evaluate it, say. And what that's approximately equal to is just the same thing here. So I haven't done anything different. I just threw the double integral sign in front of my expression. But what I'm interested in doing is actually trying to evaluate this integral on the right-hand side. And so in order to do that, we're going to do an integral over a disk. So maybe like polar coordinates make sense to use. So let's do this little change of variables where I'm going to let x minus x0 be r cosine of theta, y minus y0 be r sine of theta. Remember, dA changes to r dr d theta. And now my radius goes from 0 to epsilon, and theta should go from 0 to 2 pi. Another thing I wanted to make clear is that, remember, x and y are sort of like your integration variables here. So when you see some complicated looking things like f of x0, y0, or gradient of f of x0, y0, or the Hessian at x0, y0, like those are constants. So that's great. So like those won't change with the integral is what I mean. They're held constant. All right, so let's go ahead and do this substitution and put it into our integral. So instead of this kind of mysterious double integral over R with a dA at the end, remember we're trying to translate this into like an iterated integral where you actually have like numbers in the components. And I noticed that I didn't put any zeros on the bottom of these integrals. Sorry about that. Of course it goes from 0 to epsilon and 0 to 2 pi. And I started coloring a few things here. And the coloring is going to help me out in the next step, where I'm going to actually do like these dot products you see and this matrix multiplication that you see, so that I actually will just have like a bunch of functions, say, added together inside this integral. So the pink stays the same, but the green, you need to take that dot product, and when you do, you should get the first partial with respect to x times r cosine theta, plus the first partial with respect to y times r sine of theta. Similarly, in the gray, we're going to do that matrix multiplication of those vectors and matrices that you see, or those two vectors in that matrix in the middle that you see. And when you do that and the dust settles, you should get the following expression here, where you have 1/2 r squared cosine squared theta times the second partial with respect to x of your function, plus r squared cosine of theta sine of theta times the mixed partial xy. And then you might notice or wonder, where'd the half go? Well, there's two of those functions. Remember, fxy is the same thing as fyx, so the 2 and the half cancel. And anyway, at the very end, you get 1/2 r squared sine squared theta times the second partial with respect to y of your function. And the next step, what we're going to do is this r outside next to dr d theta, we're going to go ahead and just distribute that all the way through. So everybody's going to get an r, or like the power on r is going to bump up by 1. And notice too, oh, you see it earlier, the zeros came back as far as the bottom bounds of the integrals. Okay, good. Let's actually evaluate these integrals. So the yellow, r is the variable, and f of x naught y naught, that's constant with respect to theta 2. So this just becomes r squared over 2 from 0 to epsilon, and then you pick up a theta from 0 to 2 pi times that constant f of x naught y naught. I'm using the bracket notation to talk about how do you evaluate an integral from like a to b, like f of b minus f of a kind of thing. What's the red look like? Well, the red, you're going to get r cubed over 3, and cosine of theta changes to sine of theta. Remember, that partial derivative is just constant because you've already plugged in x naught y naught into it. The blue, similarly, changes to r cubed over 3, and then you get minus cosine of theta from 0 to 2 pi. And then the partial with respect to y is just your constant hanging out front. In the purple, so we're going to go down a line. So we'll keep adding here, though. So in the purple, we're going to bump up the power of r and divide by 4, and then cosine squared theta, remember like your half angle formulas, that should turn into a 1/2 theta plus 1/4 sine of 2 theta from 0 to 2 pi, and then you've got your constant second partial with respect to x. The green is going to look really similar. The green is a u substitution, right? If u is sine of theta, then du is that cosine, so that's just going to be sine squared over 2. And again, your fxy is just constant, so that's just hanging out. Orange is pretty similar to the purple one that we did, where you're going to use like a half angle formula. So what that sine squared integrates to is 1/2 theta minus 1/4 sine of 2 theta. And you've got your constant second partial with respect to y out front. All right, so we've done all of those integrals. And now let's plug in, our numbers. And when I do that, well, the purple, I got to start with the yellow. So we're back to the integrals, starting with the yellow. The yellow, you should just get epsilon squared over 2 times 2 pi times the value of your function at x naught y naught. In the red, you're going to get 0 because that sine term there, sine of 2 pi minus sine of 0, that just gives you 0. So times all that stuff, it goes away. In the blue, you're going to get a 0 because minus cosine of 2 pi plus cosine of 0 is going to be 0. So it's going to knock out all the blue stuff. In purple, you're going to get epsilon to the 4th over 4 times pi, and then times that second partial with respect to x. So like the sine stuff goes away. Hope you see that. And in green, you're going to get 0 because sine squared theta from 0 to 2 pi is going to be 0. And then in orange, again, the sine of 2 theta stuff is going to go away. So when you plug in these things, you should just get your epsilon to the 4th over 4, and then you should get, times 2 pi over 2. So in other words, times pi, times your second partial with respect to y. So if we clean this up a little bit and get rid of some of the zeros, I hope the color coding helped you track where the zeros came from. If I clean this up a little bit, we just said that our double integral of our function over this little disk r is approximately equal to pi times epsilon squared times my function, the value of my function at x naught y naught, plus, and if I take the purple and the orange, they both have pi epsilon to the 4th over 8. If I factor that out, then I just have the sum of these two second partials with respect to x and y respectively. And now let's pull something back in from Calc 3. You might have learned about the average value of a function over some domain, like a disk R, and that's going to be 1 divided by the area of the domain you're integrating over, times the double integral of your function over that region that you're integrating over. Now in our case, our disk R, I know its area, it's just pi times the radius squared, so pi times epsilon squared. And well, let's just go ahead and divide through both sides of this integral formula that we derived above. So let's divide both sides by pi epsilon squared. Well, on the left, you're going to get 1 over pi epsilon squared times your integral. And on the right side, if you do some cancellations with the pi epsilon squareds, you just get f of x naught y naught plus, and I think I did this right, epsilon squared over 8 times the sum of those two second partials. So in all, the average value of the function over this disk is approximately equal to the value at the center plus some scalar multiple of the sum of the second partials at the center. Great. And so again, that should not speak to you in some way. Why is this cool? We're still getting there. Taylor's theorem tells me that I could do a little bit better than just this approximation. Taylor's theorem tells me how to get an equality there. And it tells me that there's something called a remainder term that gives me an equality there. And what I'm going to do is I'm going to invoke that now. I know that I can find a point near the center, called AB, such that though, I get an exact equality here when I plug AB into the sum of those two second partial derivatives. So notice I'm changing from this average value is approximately equal to this stuff to this average value is exactly equal to this stuff. And now, what do we know about like some second partial derivatives and a function? Harmonic functions are cool because harmonic function satisfies Laplace's equation. In other words, the sum of the second partials, no matter what point you plug in, is 0. Well, let's take a look here in this formula that I have for the average value of my function. When I have a harmonic function f, up to this point I have not assumed f's harmonic, but now let's look at like, okay, what can you say when f is harmonic? You can put a 0 there. And what do? You get that the average value of your function is just equal to the value at the center. And so this is why harmonic functions are cool. We've shown that harmonic functions are such that the value of the function at the center, x naught y naught, so here's my little point, x naught y naught, the value there is exactly equal to the average over any disk centered at x naught y naught.